Welcome back to the course on architectural design of ICs. So, in the last class we have seen we are basically trying to find out one efficient architecture for computing the GCD function of two numbers. Okay. So, we have seen that based on this modified Euler's algorithm we can find out the GCD function, and there are another method also to find out the GCD function, but here we will try to find out the GCD function using modified Euler's algorithm, and then how efficiently we can design the circuit in order to, so that I can get the benefit in terms of power as well as speed as well as the area consumption. Okay, that we are seeing in the last class, and we will just continue from the. So, what we have done, we have drawn the, that means operation table, then from operation table we are just trying to find out the expression or what is the, that means what will be the architecture for that or what will be the logical expression to calculate the GCD of two numbers. Okay. So, let us continue with the that means previous class. So, in the last class where was I? I was drawing this particular function, right. So, that means this particular function means the functionality, how it works. Okay. So, based on the LSB of m and LSB of n, I can find out whether numbers are even or odd, and then based on this particular things I can what is the function I need to implement. So, that we have just made. So, here the interesting things you just see, whenever this value is 0, whatever value is for the LSB of n, that means whether that is even or odd, it does not matter. Whenever the value of m is 0, so at that time it does the same thing, that means it does the m by 2, and here also m by 2. But for odd case, it has different functionality. That means for n, whenever this is n, that means this LSB of, it depends on the changes in the LSB of n. So, when this is odd and this is n, so at that time m equals to m, but when this one and LSB of n equals to also 1, so at that time this is not m, this is another else, that means m equals to minimum of m and n. And the same things happens for LSB of n 2. That means, if you see whenever this is 0 and this is 0, it does the same thing, that means it is n by 2. So, whenever this is 1, at that time this changes, that means from 1 of m, this is minimum of mod of m minus n, for 0 that is n. So, that means now if I just that means try to reduce or try to rewrite this particular table, how can I rewrite? How I can rewrite this same table as something like this. This is LSB of m, this is LSB of n, and this is the corresponding m and n. So, if this is 1, whatever is the value, m equals to m next and n equals to n next. Okay. This is 0 and whatever value is for this, for LSB equals to m equals to m by 2. Okay. I am not putting this value, and for this is for, sorry, you do not consider this n now, this is only I am calculating for m. So, this is for 0. So, at that time if this is 1, this is 0. So, at that time m equals to what? This is m. For 0, 1 and 1, this is minimum of m and n. Okay. The same table if I just draw for n, this is for m. Okay. Now, this is I am drawing for n. So, this is LSB of m this is LSB of n and this is the n. So, for 1 cross cross this is n equals to n next, for 0 0 sorry for cross for n it is I am considering. So, n equals to n by 2 for this is 0 for whatever value is for 0 and 1, n equals to n for 0 1 and 1, n equals to mod of m minus n. Okay. So, this is the that means corresponding functions which I require for m and n. So, that means how can I implement this particular logic now? How can I implement, or what circuit I require to implement this particular logic? So, that means I need this multifunction register which can gives me this particular circuit. So, what I said that m equals to m next means, so q I that will be loaded as q next. Okay. So, m by 2 means q I will be loaded to q I plus 1, that means divide by 2. So, that means q I plus 1 means, so at that time q I if that is q 0 I value is 0. So, instead of that will be loaded the 1. Okay. Why? Because I have to divide by 2 means I have to discard the LSB position. So, one position at that time I have to load, right. So, that is why that is q I plus 1. So, whenever m equals to m means, so that is q I equals to q I, and this is minimum of n. If I consider this as a circuit C1, so that means q I will be C I. The same thing will happen for this here also, q I equals to q next, this is for n register, right. So, this is q I equals to q I plus 1, sorry this is I, this is 1. So, q I equals to q I here, if I consider this as a C2. So, at that time q I will be C2 I. So, this is C1 I, this is C2 I. Okay. So, now I have to implement this particular logic using this, I have to implement using the hardware. So, what will be the hardware for this? Okay. So, you see there are 3 control signal, but it is not that each of the corresponding, that means the value of this. So, 3 control signal means I need to implement, or here I am having how many operation? I am having only 4 operation. But if I considering 3 in as a, that means this control signal. So, at that time up to 8 function I can implement, but here I do not have the, as this is the do not care option. That means, if only this has the highest priority in this particular case. So, that means at that time the other these values it is do not use, or it is not at all used for any other function where the function will change. So, that means if I am having this 3 input control signal. So, at that time I need 8:1 multiplexer. So, but I am having only 4 function to implement. So, then why to implement, or why to go for this 8:1? Okay. So, only I can have this 4:1. So, that means I need one multiplexer where I will use these 3 control signal, but I will implement only this particular function. So, 4 of this function means only, so 8:1 multiplexer means what? I need 7 multiplexer, 7 2:1 multiplexer for implementing this 8:1 multiplexer, right. But here I need to implement only 4 function. So, that means using only 3 multiplexer, 2:1 multiplexer, I can implement this function. So, how can I do that? If I just go back and again if I just, I will just draw the corresponding, this is init, this is LSB of m, this is LSB of n, and this is m. Okay. So, for 1 cross 1 qi equals to q next, for 0 0 do not care, qi equals to qi plus 1, for 0 1 0 qi equals to qi, and for 0 1 1 qi equals to c1 I. Okay. So, now if you just see, that means it has the highest priority, after that this 0 has the highest priority, and after that it basically checks the corresponding bit position of LSB. So, now how can I implement the function? So, if I am having the 1 2:1 multiplexer, considering this, so that means now this is for LSB n, for 0 and for this is 1. So, for LSB n equals to 0, so what happens? This is qi and this is c1 I. Then this will come to what? This will come to another multiplexer where the other input is, and this will depend on what? This LSB of m. The another input of this is qi plus 1, and then if I just have another multiplexer 2:1 multiplexer where this signal is the init signal and this is q next, that you see this is for 1, this is for 0, and this is for 1, this is for 0. So, here you see how we are implementing this particular table in using this particular circuit. So, you see whenever LSB n equals to 0 or 1 and m equals to LSB m equals to 1. So, at that time init value equals to 0. So, if you follow from this, so 0 1 0 0 1 0 qi equals to qi. So, qi will be this. So, qi means this is nothing but this qi what I am considering. So, qi equals to qi. For 0 1 1 qi equals to c1 I. So, qi equals to c1 I. Okay. So, then for this particular case, for 0 0 do not care. Okay. For 0 0 do not care means if this bit is 0 0. So, 0 0 and then here it is do not care. So, that means whatever combination is for LSB, I do not have to check for the bit position of LSB n. So, that is why this multiplexer is, I have omitted that. So, for 0 0 this qi equals to qi plus 1. So, that will come here. For initial, so if this is 1 then this will be q next. So, if this is 1 it will choose directly q next, it do not have to check for the values of LSB m and LSB n. So, that means now this corresponding function can be implemented by using this kind of circuit. So, though I am having 3 control signal, but here I require only 3 2:1 multiplexer instead of 7 or 2:1 multiplexer, which I require in general, as the number of functions are smaller. Okay. So, if I just draw the block diagram of that, so at that time I will have this 4 of this input, and I will have this 3 as the control signal, which will produce the corresponding m, and the same thing for n also it will be the same, only this input values will be that means different. This is for n. So, this is init, this is LSB of n, this is LSB of n. So, here what is that? The first is, so the first is Qi, sorry, yeah, okay, Qi, then this is C1i, then Qi plus 1, and then Q next. Okay. If I just start from this, okay. So, that means the corresponding bit position you have to select, sorry, at that time what will happen, this will be, okay, whatever it may be. So, here again it will be Qi, this will be C2i, this will be Qi plus 1, and this will be Q next. Okay. So, this is init LSB n, this is LSB n. Okay. So, this will produce m and this will produce n. So, I have just done that means implemented the corresponding operation table using this. Now, what I left is that I need two circuit for C1i and C2i. What is C1i? That is minimum of m and n, and C2i is mod of m minus n. That means I have the circuit for implementing which will implement these two particular circuit. I need two circuits. So, how can I design that? Okay. So, then you first start with this, the C1, which is the minimum of m and n. So, how can I find that? How can I find that? So, if I just that means I need one comparator. Okay. So, at the time comparator means whether that will give me that, okay. So, greater than, suppose this is m, this is m. Okay. So, minimum of n I need to choose, right. So, that means I require, suppose this m greater than equals to n comparator I am choosing over here. Okay. So, after that what I need is that I am having this as a 2:1 multiplexer, and the output of this will select the corresponding values of m or n. This will choose which value I require. That means, if I find that, okay, m is greater than n, whenever this m value will be greater than of n, so at that time this will 1. So, at that time this will choose what? This has to choose this n value. That means what? if this logic is true, m is greater than n. So, at that time what will happen? This will obviously I need to find out minimum of m and n. So, that means m is greater than n. So, that means the minimum one is n. So, that means at this point this is 1, this is 0. So, now let us consider this particular circuit. Suppose m value is 5 and n value is 3. So, if this 5 and 3 compare, so this will 5 obviously is greater than 3. So, this will come to 1. So, that means this is come to 1. So, here I am having 5 and this is 3. So, this multiplexer will choose 3. So, I have got the minimum of m and n. Just consider the reverse case. Suppose this is 3, this is 5. So, at the time what will happen? At this particular comparator what will happen? 3 is not greater than 5. That means, at that time instead of 1 this will be false. So, it will come 0. So, 0 means whenever this is 0, so this will choose m. So, that means at that time 3 will come at the output. So, that means whatever is the value of m and n, by using this circuit I can easily implement this minimum of m and n. Okay, understood? So, that means this is the C1 function I have implemented. Now, what is the C2? That is min mod of m minus n. Mod of m minus n I have to find out the circuit for that. So, for that what I have to do? That means, what is I require? Minimum m minus n first. That means, I require what? I require one subtractor which is giving me m minus n. After that what I require? I require mod of m minus n. That means, whatever is the value of this m minus n, whether that value is greater than if m value is smaller than the n. So, at that time what will happen? I will get negative number. That means, the result will produce if I just do 3 minus 5. That means, this will give me minus 2. But here mod means it will not produce the minus, it will be just plus 2, right. So, what will be the logic for implementing that? Now, here I am finding out m minus n, but if m is greater, at the time again it will by default it will produce plus 2. So, here what I am doing m minus n, and then again if I am having another particular circuit where it is 0 and this is coming, this is add or subtractor, that means circuit. Here this is fully subtractor, here add or subtract, this function is add or subtract. So, add or subtract means it needs one control signal. So, this control signal will come from this particular point. Why this particular point? Because what I said that whenever this is negative, so this is the MSB of this particular, if this is let us consider P, MSB of P signal. So, MSB of P signal, how it basically works? This is at suppose, so 0 means addition, here addition subtraction logic is 0 means addition, 1 means subtraction. Okay. So, let us consider, take one example and then you consider these things. M equals to let us consider 3 and n equals to 2. So, 3 minus 2 equals to 1, positive 1. So, this MSB of P is 0. So, this will be 0 plus 1, which is 1. If you consider m equals to 2 and n equals to 3, so at the time what will happen? The P equals to minus 1. So, minus 1 means the MSB of P, that is equals to 1. So, 1 means it will be 0 minus of whatever results I am producing. So, 0 minus of minus 1. So, that is equals to 1. So, that means now I can develop the, that means using this particular circuit I can implement the function of mod m minus n. Okay. So, what we did? We have implemented the C1 circuit, we have implemented the C2 circuit, okay. C1 and circuits and C2 circuit we have implemented. So, output of this is C2 and this is C1. So, the corresponding bits of that will be connected where? To this particular positions. So, C2 will come here, the output of C2 that will come here, and the output of C1 circuit that will come over here. So, this is not the, this is for, this is M register and this is N register. So, this is that means the basic blocks we are just building to find out the ultimate circuit. Okay. So, this is the blocks. Initially what we are trying to do, initially block wise we are trying to implement, and then finally we will integrate all of this to calculate or to achieve the final circuit of GCD of 2 numbers. Okay. So, for today's class this is it. In the next class we will continue from this particular point and we will try to build the final circuit of GCD of 2 numbers. Okay. So, thank you for today's class.